Hi ladies, happy first e-learning lesson, woo woo. So we are gonna keep plugging away. Chapter 6, remember we're still talking about radical functions and rational exponents. And we left off right before spring break talking about graphing square root functions. So we're just gonna jump right into graphing cubed root functions. So before we begin, I do want to take some time to talk about our cubed root parent function. So if you follow those links, and I should have pulled this up ahead of time, but did I? Nope. So if you follow those links, then you can see your cubed root functions. There we go. So this is the one that I called the transformation. So we'll kind of talk about this all together. But notice instead of just being kind of that half increasing function, right, that our square root was, that now we have both halves. And remember, that kind of makes sense to us because you can take the cubed root of positive and negative numbers. So whereas our square root functions all kind of stopped, right? Because they all had a starting point or a stopping point, whichever. Our cubed root functions are going to go on and on. They're just going to kind of swivel in the middle. And they're going to go on forever, left and right. So just like always, our a, h, and k values are going to do the exact same thing they've always done. So your h is going to transform you left and right. Your k is going to move you up and down, which is a vertical shift or vertical translation. And your a is either going to stretch if it's bigger than 1, compress if it is less than 1, and then of course if it's negative, it's going to reflect it. So it's going to be decreasing the entire way. So let's go ahead and summarize this. And I updated your note sheet, but I did not update mine. So if a is less than 0 is what that should say. That is going to be, as always, your reflection. And honestly, you can just copy this from our notes from day 1, where we were talking about square roots, because it's the same rules that apply, right? So if a is between 0 and 1, that is a vertical shrink or vertical compression by a factor of a. And then if a is greater than 1, again, ignoring the negative, that's going to be your vertical stretch by a factor of a. If h is positive, that is a horizontal shift or translation to the right. But if h is negative, that is a shift to the left. And then when k is positive, that is going to be a vertical shift up k units. And if k is negative, that's going to be a vertical shift down k units. Now, this time, our domain and range, as opposed to worrying what h and k are, remember, if your graph goes on forever, left and right, then that means our domain is all real numbers. Our range is all real numbers. And for fun, let's put it in interval notation as well, because that's a good reminder for us. It's going from negative infinity to positive infinity. So our first example, we're just going to graph our parent cubed root function and state the domain and range. So here are our new points. Now, cubed root functions, there are 5 points we need to remember. 0, 0 is our one in the middle, okay? And then 1, well, what's the cubed root of 1? 1. And then what's the next number that we can take the cubed root of? 8. Cubed root of 8 is 2. But now remember that this time you can also take the cubed root of negative 1. You can get a negative 1 when you cubed root negative 1. And then the other number must be a negative 8. The cubed root of negative 8 is negative 2. So we will plot all of those points, and it looks something like this. So notice that it's kind of really steep right there in the middle, and then it really slows down how fast it grows after that. And it doesn't level off. It kind of looks like it does, but that's just because we're limited in how we can draw. But notice that it really does keep going up and up and up forever and ever. So here is our parent function. Our domain then is going to be all real numbers, and our range is going to be all real numbers. So these are the parent points that we need to memorize that we're going to transform from here. And then remember that our square root ones were slightly different, which makes sense. It's a different function. But we are going to jump into it then. Graph the cubed root functions and state their domain and range. Describe the transformations. So let's start first by just throwing our parent points down so we don't forget. So we've got -8, -2, -1, -1, 0, 0, 1, 1, 8, 2. 5 points to remember this time. And then our transformations are going to tell us how we're going to be moving. Well, that A being -1 tells us that we are going to have a reflection. And that is going to change our y values, remember. Under our square root, we have an h equaling +1. Don't forget it's always the opposite sign of what we see. So that is going to be a horizontal shift to the right one. And if we're moving left and right, that's going to affect our x coordinates. So let's transform those first. If we are moving to the right one, then we take each x coordinate and we add 1. So we've got -7, 0, 1, 2, and 9. Throw those old x coordinates out the window. And then we will do our reflection next. That's your y coordinate transformation. So you just take each y coordinate and change the sign. Basically, you make it negative. So +2, +1, 0, -1, and -2. So interestingly enough, same numbers, just in the reverse order. So these points that we've got, well, we have the ordered pair -7, 2. So we'll start there, -7, +2. And then next we've got the point 0, 1. We've got the point 1, 0, 2, -1, and 9, -2. So it should always kind of follow this pattern. And so if when you're drawing it, it's not quite looking like that, check your transformations. And there's our good enough cubic root function. Our domain and range, always, 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 for cubed roots, will be all real numbers. Excuse me. So now we'll move on to our next problem. We are still going to start with those same parent points. So we have -8, -2, -1, -1, 0, 0, 1, 1, 8, 2. This one has all sorts of transformations happening. So our x's are going to be transformed because we have a horizontal shift left, 2, because h is a -2. So that is going to move our x's to the left 2. So we subtract 2 from each x coordinate. -10, -3, -2, -1, and 6. Throw those old x coordinates out the window. Now this one's going to have 2 y coordinate transformations. Remember that you have to do A before K. It's alphabetical. Or think of it as PEMDAS. So if A is a +2, that is going to be a vertical stretch by a factor of 2. So we have to do that transformation first. So take each y coordinate, multiply by 2. We've got -4, -2, 0 times anything is still 0, 2, and 4. And then we can apply that K transformation, which is going to be a shift downward. So shift down 3. So we'll take each y coordinate and we subtract 3. Now -4 minus 3 gives you -7. -2 minus 3 is -5, etc. So -3, -1, and +1, right? Yeah. So cross out all of your old y coordinates as well, and you have your new ordered pairs. So we've got -10, -7. So left 10 and, okay, down 7. Next point is -3, -5. So we move left 3, down 5. -2, -3. -1, -1, and +6, +1. So this curve is a little bit steeper, which checks out because it is a vertical stretch by 2. Good enough. And what is our domain and range for this? All real numbers for both. Okay. Lastly, we have ourselves a word problem. Of course we do. Biologists have found that the shoulder height in centimeters of a male African elephant can be approximated by this function, where t is the elephant's age in years. We're going to use our graphing calculator to graph the model, include a sketch of your screen below, and determine the age of an elephant whose shoulder height is 200 centimeters using the intersection feature. This one's new. Alrighty, so we are going to start by plugging h of t in for y1 of our graphing calculator. Alrighty, so we want to go to the y equals of our graph, or of our graphing calculator, so we can plug this in. And our equation was 65.8 plus, 75.8 plus 62.5. Okay, 75.8 plus 62.5. Also, notice that we cannot combine those because the 62.5 is attached to our cubed root. Now, your cubed root you can find under your math button, as always. So we'll go to math, and option 4 is the cubed root. So times cubed root of x, or cubed root of t, according to our equation. Now, when we consider our windows, then we need to think about what our x and y were standing for, or I guess we had t and h of t, but tomato, tomato. So t is the time, or the age of the elephant in years. I think elephants can be pretty old, so I did 0 to 70. We're going to see what that ends up giving us, and then we'll count by tens. And then the y, min, and max, well, it's the height in centimeters, so we know that 0 would have to be a minimum height, right? But in terms of how tall they can actually get, centimeters aren't very big, remember? So think about how many meter sticks tall. Well, 300 centimeters is only 3 meters tall, 3 meter sticks. So I think that's pretty reasonable for right now. And then I said, well, let's even do count by 50s, why not? And then we'll go to our graph. And notice that we can only see half of our graph, right? We said that our cubed root functions always kind of make that swivel shape, but we basically just cut off all of the negative part, which checks out because time cannot be negative, height cannot be negative. So this is what we have so far. Next, we are asked to find how old an elephant would be if they're 200 centimeters tall using the intersection feature. So if we go back to our y equals, now 200 centimeters is going to be a y coordinate, right? That's a height. So we're going to plug in just 200 because we want to know when y is 200. We'll do it as a separate y equals, and we're going to go back to our graph so that we can get this sort of shape. And we still have our cubed root, but now we have this horizontal line. Our job is to find out what that point is where they intersect. So remember that pretty much anything we do from our graph screen, in order to do something other than just trace, we always click second and then trace, right? And sure enough, option 5 is intersect because we want to know where those two curves intersect. Then it's going to ask us, hey, what's your first curve? Y1, yep, we want that, so we're going to hit enter. Y2, well, yeah, it's that guy, yep, checks out, hit enter. And then as we guessed, you can either arrow left and right, or you can estimate, right? Remember, now I can't even remember, I think we did each tick mark on our x's stood for 10. So it looks like it's just shy of 10, right? So maybe like 9 for an x coordinate. And sure enough, 7.8 wasn't even close. So 7.8 for 7 years old, right? At 7.8 years old, it's going to be 200 centimeters tall. So we will pull up a graph of that and draw a real quick sketch on our notes, and then make sure that we indicate our windows. And then from there, we're going to be good to go.